call is now being recorded. So this is lecture 2. Black body radiation, and today is the 10th. Okay. So what I want to show is that in Rayleigh-Jean's law, the average energy per mode is kT. So how do you calculate an average energy? So these angular brackets, they normally mean averages in quantum mechanics. But also in classical mechanics and statistical mechanics. So you might have encountered it before. And then you multiply every possible energy with the probability of having that energy, okay, over the small interval of energy. You integrate it over the range of possible energies, and you divide it by the total probability. So here actually this is a probability distribution function. If it is a normalized function, then of course the denominator is 1. But when it is not normalized, you have to divide by the total integrated probability in order to have a average energy per unit energy in a way. Okay? And we want to show that this is equal to kT. Is it? So in our case, if we have a black body and there is a classical distribution of energy for the standing waves of the black body, then we can use the Boltzmann probability distribution for the possible energies, not possible energies, but the number of standing waves for each energy in the black body. So use Boltzmann probability distribution.
Ma'am, how do
Yeah.
we arrive to the fact that we will use Boltzmann probability distribution only? Means why can't we use any other probability distribution?
So this is basically, so if it's classical physics, then when you have a heated body, then the possible or let's say, so this is the only distribution that we actually have, but that relates the energy to temperature, and that is what we want, right? The energy distribution for a given temperature, you have it's only the Boltzmann probability distribution. It's not anything else.
Oh,
Yeah. So we use the Boltzmann probability distribution, and then that tells you that the number of standing waves for any energy E is given by e to the power minus E by kT. So this is, you are familiar with this distribution, I guess. Okay. So then our task is to evaluate this average energy. So how do you do that? You take the average, we just substitute everything. So 0 to infinity by okay. So let's look at the form of these integrals. So I can write so if I say E is my x variable, then x e to the power minus ax dx. Here, what have we considered? That a is equal to 1 by kt and x is equal to e. Okay. Then, how do you integrate this? So we can rewrite this a little bit by doing this, that you have 1 by a 0 to infinity ax to the power minus x dx. So what does this look like? So this looks like 1 by a integration 0 to infinity z e to the power minus z, and if ax is equal to z, then dx is equal to dz by a. So I have 1 by, this was d, this is then dz by a. So I have 1 by a square infinity z e to the power minus z dz. And this is more or less a familiar integral which you integrate by parts. So let's integrating by parts. So everyone is familiar with integration by parts, I guess. I'm not writing the formula, I'm just directly going to the derivation. So this is first function, second function. So first function, integration, second function, minus integration, derivative of first function, that's 1, integrand of second function, and then another dz. This is equal to 1 by a square. Minus z e to the power minus z, and here I have minus integration e to the power minus z by minus 1, so dz. Okay, so I'll put the limits later. Let me just do it like this. Square. Plus, no, again minus. So when I integrate this, I'll get another minus. So it remains minus. So minus e to the power minus z. Then I can take e to the power minus z common, and also the minus. So minus a squared 1 plus z e to the power minus z. Fine. Now let's put the limits. Then I get minus a square z e to the power minus z 0 to infinity. That is equal to so when I put z equal to infinity in the first term, I get e to the power minus infinity, which is 0. And when I put 0, I get 1. So this is basically equal to minus 1 by a square into minus 1. That is 1 by a square. Okay. 1 by a square. So, and then now when I use the and remember, a is equal to kt, therefore 1 by a square is equal to kt square. Now, we also have to evaluate the denominator.
Ma'am, A is 1 by kt, right?
Yeah, sorry. That's what I use. I just wrote it wrong. Yeah, 1 by kt. Yeah. So then 1 by a square is kt. Sorry. Okay, and then we need to also evaluate the denominator. That is, this is a simple integral. So you just get minus 1 by kt inverse, so that's minus kt. And you have e to the power minus e by kt, which goes from 0 to infinity. So that is equal to minus kT into 0 minus 1, and that is equal to plus kT. Okay, simple enough. Then average energy expression. I'll put a classical subscript over here because this is from the Boltzmann distribution. And you have kT squared as the numerator and kT as the denominator. So the average energy is kT. So now you see that the average energy per mode, so the per mode comes because we're dividing by the total distribution. For every for the standing waves in the black body is kT. So this is the derivation, and it is this probability distribution function which will change when we derive the Planck's law. So let's do that next then. So the next thing we'll do is derivation of Planck's law.
Ma'am,
Yeah.
ma'am, that KT is classically it is the energy of the oscillations of the molecules and things like that, right? And on the walls of the black body.
Yes. So there are two ways of thinking about it. So when you have a standing wave, then the average energy per mode of a standing wave is kT, and then you multiply it by the number of possible modes, and you get your spectral energy density finally, like we did before last class.
Yes, ma'am, but still, I mean, could you explain the relation between, because it's light, right? The standing waves are of light, and light, light cannot
It's
possess
valid for
temperature.
light as well. So here, classically, there was no difference between the a light and a mechanical standing wave. I mean, you treated it with the same physics machinery. It's only after you have Maxwell's laws and then followed by quantum mechanics that you could that you had a different description for light, that it was different from mechanical waves in some ways. But before that, classically, light is just a wave. I mean, you didn't know about the electric magnetic fields, at least when Boltzmann
Ma'am,
came
but
up.
how can it have a temperature? That's what I'm asking. It can't have it, right? I mean, there's nothing
No,
to
it
possess
doesn't.
temperature.
No. Like I said, this is a subset of radiation. So it's not that each individual light has a temperature, but given a emitting body of a certain temperature, the average energy emitted from that body in the form of light is kT.
Oh, okay,
So
okay,
yeah, so it's not that the light itself has an average energy of kT.
okay, got it.
Yeah. So if you have a different body, this average energy will change if it's at a different temperature, for example. So this average is not for the light itself; it's for the body emitting the light. So this is what I was not clear about last class, leading to all the confusion, I think. So I hope it is clear now. It is the average energy emitted by the black body in the form of light. I think that solves the problem. Okay. Now for
Okay,
Planck,
ma'am.
yeah. Okay. So what did Planck propose? He
So,
proposed a very
ma'am,
yeah. Go ahead.
ma'am, in the subscript of average energy, what is written over there?
It's CL for classical.
Okay, okay, okay.
Yeah.
Thank you, ma'am.
Yeah, I'm sorry, my handwriting is a little bit bad on the tablet. Otherwise, it's not so bad when I write on paper. But, okay. So now for derivation of Planck's law, what was the difference that Planck proposed? So the Planck's proposition was that not all energies or are allowed for the standing waves in the black body. So what he proposed was that you don't have a continuous spectrum for E. You have, this was Rayleigh Jeans, but you have a discrete spectrum. So this was Planck. So what does that mean? That means that instead of writing an integral over E, so that when you're writing this average energy, let's say Planck, okay, then instead of having an integral from 0 to infinity, you have a sum from 0 to infinity, and the possible energies are all multiples of h nu. So he proposed that the energy of the standing modes were quantized in terms of h nu. Okay, and this was the crucial point, and this was multiplied, of course, by a probability which depended on of jh nu, let's say, and j was a series of discrete numbers from 0 to 1 to 2. So it's a discrete spectrum. You also divide by the sum from 0 to infinity e to the power, write that now, probability of jh nu. So this is j equal to 0 to infinity, j.
Ma'am, what is P of JH nu?
So this is the probability distribution function for this. I can write this as E as well. So this is the same as the probability of having each energy, just that now not all energies are possible, only multiples of h nu are possible.
Ma'am, is it that probability of that energy?
Of that energy, of this energy.
Of that energy, where, ma'am?
So this is the distribution function for every possible energy.
So does that mean that the probability of existence of that energy? What does it mean?
This tells you have how many modes of that energy in the black hole.
Okay.
Well, not. Yeah, sort of. Yeah. So this is same as before. It's just the difference is going from a continuous spectrum, you're going to a discrete spectrum, meaning you cannot have all possible E's. So both your distribution function and your energy itself is discrete. So you have to sum over them now. You're jumping.
So, ma'am, it is the probability of modes with that energy E.
Yes.
Is that it? Okay.
Yes. The energy range is still from 0 to infinity, but not all the values in that range are possible. So J is only so the energies are only integral multiples of h nu. So this is what he proposed, and what he introduced h, which is Planck's constant, which is called Planck's constant. Okay, and this was a constant that he multiplied to the, you can call it sort of like a fundamental frequency, to give you the unit of energy by which every energy level in the black body differed. Okay. Let's see the implication of this first, and then we can try and understand the physics again once more. So if I let e to the power minus h nu by kt be equal to x, then e to the power minus jh nu by kt is simply x to the power j. So now our task is to evaluate the values of series. So let's do the denominator, which is a simpler series. So the denominator is basically then equal to 1 plus, oh sorry, I skipped something. I should tell you that we're again going to use the Boltzmann distribution, but in the discrete form. So that part doesn't change. The black body is still classical, okay, for Planck. So the energy distribution is still the Boltzmann distribution. So let me see if this works. I can shift it down maybe. Okay, this works. Then P of JH nu, that is still e to the power minus JH nu by KT. So this is still Boltzmann distribution.
Ma'am,
Yeah.
can you please scroll up for just 1 second? I could not copy one line.
Scroll up, you mean? Like here?
Yes, ma'am, just 1 second.
Okay, sure.
Okay, ma'am, it's done. Thank you.
Yeah. Okay. So then,
Ma'am,
yeah.
ma'am, how do we know that the Boltzmann distribution is also true here? Because in the Boltzmann distribution, in this derivation, some energies, I mean most of the energies except those which are quantized are ignored, right?
Yes. Yes. This is not a continuous distribution.
So
But
some energies are ignored, so the probability, I mean, won't be. I mean, some probabilities are excluded, right? Some energies.
some energies are excluded. That is right. But the black body itself is classical. So this is the probability distribution. This tells you for each energy, and now we're selecting out of this distribution some energies. It's not. So you see, it's. Let's say how to put it.
Ma'am, if those energies don't even exist, then how can we say that they have some probability and we select out of those? Can we do that?
Whether the distribution itself changes, that is, so that would depend upon whether the black body is classical or quantum. But so what Planck did, so the only energy distribution that we know is the Boltzmann distribution. Okay, so this comes from the distribution of the kinetic energy of the particles. So it's actually, the source is not even a black body, but that is the distribution which is applied to all objects, all thermal objects emitting radiation, or even just like what should I say? Like even if you're not considering any sort of emission, even just energy levels of like for gases, you have the Maxwell-Boltzmann distribution. So that is again just the energy of the molecules in the body. So it's the only one we know basically.
Ma'am,
Yeah.
actually my question was, in the Boltzmann distribution, every energy has some probability, right?
Yes, so I get your point. You're saying that
But
now that the energy is redistributed and maybe the distribution is something different. That's your point, right? I understand your point.
ma'am, can you please repeat what you said? I just lost.
So your point is that if some energy levels are disallowed, then the total energy is simply redistributed in some way among the allowed modes. That might mean that the distribution no longer looks like a Boltzmann distribution, right? That is what.
Ma'am, then the probabilities will vary, right? Then it's no longer a Boltzmann distribution.
Yeah, then it's no longer a Boltzmann distribution.
Man, then why are we using Boltzmann distribution here again then?
So this is how Planck proceeded. So he said that this is because again this is the distribution we know. It's not. So if you take, I'll tell you the thing. So if your system is like an atomic system, okay, where there is quantum mechanics involved, then it is no longer a Boltzmann distribution. Okay, but that we found out much later.
So what we are doing right now is also wrong, in a sense.
It's wrong in the sense. Well, it is applicable to the black body radiation. So the expressions that we get are good enough for black body. You can, of course, correct it further by using quantum mechanics.
Ma'am, your voice is too low, ma'am. We can't hear it very clearly.
Oh, you cannot hear me?
Ma'am, we can hear, but it is a little low. So.
Okay, well, I don't know what to do about
Ma'am, it's fine now. It's fine now.
Okay, so the thing is that yes, if you wanted to describe black body radiation entirely in terms of the perfect thing, that is what actually S.N. Bose did much later with statistical mechanics, and that was not a Boltzmann distribution. Okay, so if that is your question, yes, it is possible to do it more correctly, but this was good enough to explain the experimental spectrum. Because
okay, ma'am.
So there are lots of them, right? Almost considerable.
So are we just assuming that the Boltzmann distribution is also applicable for in quantum mechanics, and we are also getting expression by using this distribution, so we are doing it anyway. Is that correct?
Yeah, you can say what we are doing is we are following Planck, what he did and what he achieved. We are not going for the perfect derivation.
Okay.
So you can do a perfect derivation as followed by S.N. Bose, for example, and then S.N. Bose, sorry. Yeah, I'm not wrong. S.N. Bose, and then he did it in the correct way.
Ma'am, do we do that in this course?
No, we don't.
Okay, ma'am.
No, we don't. Maybe in quantum physics, when you do Bose-Einstein condensate, if someone teaches you that, like how to get the Bose-Einstein condensate, you will do that.
Okay.
So this takes into account the fact that you have photons and they are bosons, like I mentioned. Did I mention in this class? Probably. And then the statistics that the bosons follow, and then it does some. Then you go on with the derivation. But here we stick to the Boltzmann distribution just like Planck did. Then you have a denominator. So then let's evaluate the denominator. So we have to evaluate two sums. So I'll show. So this is this. So JH nu. Then P JH nu is e to the power minus JH nu by KT. And in the denominator, we just have a sum over e to the power minus JH nu by KT. And I have said if I let e to the power minus h nu by KT be x, then e to the power minus JH nu by KT is x to the power j. So I'm just going to evaluate the sum.
Ma'am?
Yeah.
Ma'am, I still didn't get why we are getting correct answer even though we are using a wrong distribution.
Because it's almost correct. I mean, you have a large number of modes, like I said, and then if the fundamental frequency is low, then like JH is almost correct. Good enough. H is a fairly small number, right? H is 10 to the power minus 34.
Yes.
And the frequencies maybe 10 to the power minus 10. So if I say or 10 to the minus 7 meters of the order. So this h nu quantity is a really small quantity. And multiples of that, if you have a series, then it's almost a continuous series. So that's why it's good enough.
Okay, ma'am.
Yeah. But you'll get a very stark difference. You'll see as we go along in the expression for the average energy, and that will take care of the ultraviolet catastrophe that was the problem with the classical description. So you'll see that it makes a difference, even though we are not doing something that's terribly different. The fact that you evaluate a sum and not an integral makes a difference. Okay, so this is the denominator, x to the power j. So that is 1 plus x squared. Okay, an infinite series. So this is a geometric infinite series, and the multiplying factor is x. So by that rule, you have 1 by 1 minus x, the value of the sum. Now let's do the numerator.
Ma'am,
Yeah.
while we are taking the summation, we are still taking each and every point into consideration. So how come are we signifying the discrete characteristic that Planck gave?
We're taking but we're taking a sum, right? So we are taking only multiples of h nu as allowed energy. So any energy which is not a multiple of h nu is excluded.
Oh, okay, that way. So every value of j is considered, right?
Every value of j is considered. Yes.
Okay.
So that tells you that you have the range of allowed energies is the same, 0 to infinity. In this range, you are excluding those energies which are not multiples of h nu.
Okay.
Okay. So then in the numerator, let's see, that is equal to h nu sum j equal to 0 to infinity j into now x to the power j. So this is again another series. So h nu into this, the first one is j equal to 0. So this the first term is now 0. Then the next it's j equal to 1. You start from j equal to 1 then. That's x. Then plus 2x squared plus 3x cubed plus dot, 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 dot. This is equal to then h nu x into 1 plus 2x plus 3x squared. So do you all want to try to evaluate this yourself?
Ma'am, that will be 3x square, right?
Yeah, 3x squared, yes. Do you want to try to evaluate this yourself now? I can give you 5 minutes to try.
Ma'am, can you please go a bit upward for the denominator part?
Yeah.
Okay, ma'am. Thank you.
So use the expression for the denominator.
Ma'am, it is binomial expansion for 1 minus x whole power minus 2.
Yes, that's right. So if you know that already, then no problem. Then you can directly use it. So this is then x, and you have 1 by 1 minus x whole square. So now we are in a position to write down the average energy per mole as predicted by Planck. So we put the numerator, and you have the denominator. This is equal to then h nu x by 1 minus x. And if you remember, try and put this on the same page. Then this is h nu by 1 by x minus 1. This is equal to h nu by e to the power h nu by kt minus 1. Okay. So this is fine. So what is the difference now? Let's look at the two average energies. So we did the
Ma'am,
yeah.
I'm not getting how we got that 1 plus 2x plus 3x square, that expansion to be 1 by 1 by 1 minus x and so on.
Okay, I can show that, no problem. This is fine. I'll just do a side note here then. So let's say my S is 1 plus 2x plus 3. My tablet doesn't scroll very well. Okay. So 1 plus 2x plus 3x squared plus whatever. Okay. So I can multiply this with x, or wait 1 minute. Yeah. Let me see if I remember my high school math. 3x cubed plus whatever. And I had so 1 by 1 minus x is equal to 1 plus x plus x squared plus whatever. Then I subtract, yeah. So this, if I say this is equation 1 and equation 2, then if I subtract,
No, ma'am, you'll have to do the first one.
Ma'am, we can just
The
differentiate
top
the
one.
two equation. I mean, the number two equation, we can differentiate it to get that expansion.
yes, that also you can do. That is also
I mean,
a
you'll have to
good one.
subtract the extreme top one and the one you have written one. That.
Ma'am, we should do S minus Sx
S
to get.
minus Sx. Okay,
Yes.
okay. Right. So there are two ways of doing it. So I got two suggestions. So let's do S. So 1 minus 2. So S minus Sx is equal to what happened? Oh, S minus Sx is then 1 minus x. Then oh no, this is not the way. 1 second. This is then 1.
Ma'am, it will be equal to 1 by 1 minus x.
So
1 plus x, since it's 2x minus x. Like
2x
that.
squared. No, this is no 1. S minus Sx is not right.
Ma'am, S minus
No, you
Sx is
have
1 by
to
1 minus x.
It's 1
It will
by
be 1 minus x.
1 by 1 minus x. So I should get back. Oh yeah.
So
Right.
we will
1
get yes, right?
Yeah. I was not being careful. 1 minute. Sorry. So this is 1 plus x. So I'm subtracting 1, and then 2x minus x is x. 3x squared minus 2x squared is x squared. That's fine. So then this is s into 1 minus x, and this is 1 by 1 minus x. Right. So s is equal to 1 by 1 minus x. And this is simple enough. And the other option was to differentiate this expression. Then also you get the same thing. Okay. So now it's clear. Whoever asked the question before.
Yes, ma'am, thank you.
I'm sorry, I don't realize who is asking what question.
Ma'am, can you please once show the denominator part?
This
Yes,
is
ma'am. 1 minute.
So this is a very simple geometry. Multiplier as x.
Yes, ma'am, done. Thank you, ma'am.
Okay. So this is it. So where were we now? I got a little bit distracted. Okay, so we got the average energy for Planck as this one. Okay. So let's see how it differs from the average energy we got before. That was simply kT. Okay. So here there is a sort of a modulation of this factor. So let's see. But we have still not got up to the expression for spectral energy density. So let's go there. So the next thing is the, I was writing it in green, right? Yeah. So the number of modes between nu and nu plus d nu. That is this counting that we did last time with the sphere and the lattice point. That remains the same. Okay. So this is the same for classical Rayleigh-Jean's theory and Planck's theory. Let me just write the expression then, since we derived it before. So this was n nu, or the average one. This was, so when it's average, you just d nu is equal to 8 by nu square d nu by c cube. So this was what we got before. Now we go to the spectral energy for Planck. Spectral energy density. So the spectral energy density U nu T at a temperature T for frequencies in the range nu to nu plus d nu. This is equal to number of modes per unit volume. So I've divided by a cube. Okay, so that's why I've put the bar per unit volume in nu to nu plus d nu. So you multiply this with the average energy per mode. So when we did Rayleigh-Jean's, what did we get? We got U nu T d nu is equal to pi 2 by c cube nu square d nu into kt. Okay. And that gave me 8 pi nu square by c cube simply into kt. Now when I do Planck, U nu T d nu is equal to the same quantity. So 8 pi nu square by c
Ma'am?
cube. Yeah.
Ma'am, there should be a d nu as well.
Yes. Here. Right.
Ma'am, it is cancelled, right? Both sides. Will be cancelled.
Oh, sorry. Yes. Yes. Yes, it is. Right. Yeah. So this d mu
But
is
ma'am,
basically
if
a
you are
little.
mentioning U nu T d nu, then we should write a d nu on this side also.
Yeah, we wrote it and then okay. So this is u nu.
Yeah, then we do need to write.
Yeah. So you be careful, even though I am not at the moment. So we want the expression for the spectral energy density. Okay, so that is just the function u mu t. Okay, and this one is yeah. So d mu. This is again the same quantity as before, and I multiply with h nu by e to the power h nu by kt minus 1, and that gives me u mu t, no d mu, as 8 pi nu cube. I can have the h if I like. Shift the h. Looks nicer if I put all the constants together. Nu cube by c cube, and you have a factor, this. So this exponential factor that is multiplied to this quantity makes all the difference uh, for Planck. So what is happening? Let's see. So what was our ultraviolet catastrophe? Our ultraviolet catastrophe was because we had just a proportionality with nu square, which means that for high frequencies, the energy density became really high. So which meant that as soon as you heat a black body, uh, a very, very large portion of the energy will be emitted as high frequency radiation, and you will have like a tremendous like UV blast from this black body. This is of course very strange. I mean, you don't observe it experimentally, and even intuitively you don't expect something like this to happen, right? So that was the problem with nu square. In case of Planck, what Planck derived, you of course have a nu cubed, so that would make the UV catastrophe even worse. But you also have this modulating factor, and this is the important part. So what happens? So whenever you have h nu for very large frequencies nu, then this factor becomes very large, the denominator factor. Okay, and since this is an exponential function, it increases at a faster rate than nu cube. So it damps out the dependence on nu cube. So in terms of, so mathematically, as you go to larger and larger nu, the denominator starts becoming much larger than the nu cube in the denominator. And that is what you say, that the exponential factor in Planck's law damps the nu cube dependence in it. And this results in getting also the maximum. So you see the spectral energy density from the Rayleigh-Jeans law will not show any sort of maxima at all. Okay? The maximum will be at infinity. And the value of the energy density at infinity will also be infinity, which was not right, of course. But you can find a maxima for this Planck's distribution law. Okay. So let's do something else. We'll try to see in what limit Planck's law goes over to Rayleigh-Jeans law. So this is the next thing. So you saw that we only made a very small change in the derivation, but it resulted in quite a remarkable change in the final function. Yes?
Ma'am, could you just repeat the maxima part once? I mean, actually, your voice is coming very low.
Does everyone have the same problem? I mean,
Yes, ma'am, your voice is low.
do you have any suggestion about what I can do? I mean, my mic volume should be fine, I guess. Okay, I'll have a look at it after this class because I don't. Let's see. Do I have some settings somewhere? But this is just your volume. It's not my volume. can't even find my settings. Okay, settings. Sounds. No, I don't see any option to increase mic volume. I'll try and see what is happening later. Okay. I'll just speak loudly for now. Okay. So where were we? So we were going to see if we can get Rayleigh-Jean's law from Planck's law. Rayleigh-Jean's law from
Ma'am, before that, could you explain that maxima part again once, please?
Oh
Yes,
yeah,
ma'am.
sorry,
Even I
sorry.
could not
So the
hear that.
maxima is so here you have two competing factors in the expression, the numerator and the denominator. So if so, you can actually find a finite maxima for this function. In fact, either you can try and work it out. I mean, you just need to differentiate and set the first derivative to 0, and you will get the frequency at which the spectral density is maximum. But for Rayleigh-Jean's law, you can just look at the expression and see that this has no maxima. This is just an increasing function with you. So the maxima is basically at infinity. Unless you have like competing factors, things which increase the function and things which decrease the function, like parts of the function, then you can have a maximum. If you don't have any competing factors, then it's either just an increasing function or a decreasing function, and you will not have a maximum. So that was my point, that in the experimental plot, remember, we did have a maximum. And this the value of the frequencies at which this maximum occurred, these were related by Wien's law to the temperature of the system. So this Wien's law is also derivable from Planck's law. Rayleigh-Jean's cannot give you Wien's law. So I'll maybe you can do that for an assignment, or I can also work it out if you like. So we'll see how Planck's law sort of fits in with other experimental observations. So let's see when it becomes the Rayleigh-Jean's law. Then we'll see how it gives us the Wien's law. So the limit for no, okay. So the limit for getting the Rayleigh-Jean's law from Planck's law is when kT is very much larger than h nu. So like I was saying, the distribution, if h nu is really small, I mean it is as such really small in a general case, but when it is really small compared to kT, that is when you get a classical behavior for the energy distribution. Why is that? So mathematically, it is because then h nu by kT is very much less than 1. If h nu is very small compared to kT, then the numerator is very small compared to the denominator, and this fraction is very much less than 1. In that case, you can approximate e to the power h nu by kT as 1 plus h nu by kT plus, okay, so you have these, so you have the exponential expansion, and you can stop, let's say, at the first term, because h nu by kT is very much less than 1. So h nu by kT squared is even lesser, and then all the other terms become insignificant. Okay, then so we have this factor. So then e to the power h nu by kT minus 1. which is the factor we have in the denominator of the spectral energy density, that can be approximated as h nu by kT. Okay. And if we do that, then the spectral energy density expression, it becomes 8 pi h nu q by c q 1 by h nu by kT. Okay, then I can cancel all this and we are back to Rayleigh-Jean's expression.
Ma'am, ma'am,
Yeah.
I have a very silly question. Ma'am, in like when Rayleigh-Jeans came up with this law, the experimental curve came after that. I mean, first the theory was proposed.
Uh, well, no, I mean the theory was just the classical theory. But after the experiment, Rayleigh-Jeans tried to explain this experiment with classical theory, and then he came up with this absurd expression.
But ma'am, then he must have known that his expression is wrong by looking at if the experiment was performed before.
Yes, he knew. He knew. Of course, he knew. He
Then
was
why-
aware of this, but then that led to the conclusion that there must be something wrong with the classical theory, because you see, he did not make the mistake. He used the classical theory, which led to a wrong expression. So until Planck came up with this very radically new way of expressing the energy distribution, it did not solve the problem. I mean, as long as you stuck to this continuous energy distribution concept, you cannot get a correct expression that fits experiment. And classical theory means that you have a continuous energy distribution. So he actually found the problem in a way. It was not that he was, I mean, he knew it was, the answer was wrong. But it was not he who made the mistake.
Okay, ma'am.
Yeah.
Thank you, ma'am.
Yeah. So this is the this is a simple limit thing. So as soon as you take h nu to be really small compared to kt, you can truncate the exponential series and you get back to Rayleigh-Jean's law. That's simple enough. Then the next, so like someone was asking about the maximum. This is part 5, so this is part 6. So let's see if we can find this lambda max. So we can do Wien's law from Planck's law. So Wien's law gives you this relation that lambda max into T is equal to a constant. Okay, I forgot the value of the constant. Sorry. This is Wien's law. So it tells you that this is a constant. Let me just write constant, otherwise someone will think this is the velocity of light. Okay. So this was Wien's law, that the maximum at spectral density at a given temperature is related to the temperature, and this maximum shifts with change in temperature of the black body. So can we get this expression from Planck's law? So let's first shift to the wavelength form of the Planck's law. So I have in Planck's law we have expressed everything in terms of u nu t. So now let's go over to u lambda t, okay? And then we'll find the maximum directly. So what is u lambda t, t lambda? This is equal to 8 pi h pi. So now Okay, let me, do we have that expression here? Okay, so we have 8 by h by c cube and then new cube on top. So I can write every nu as c by lambda. So then, or I can say that nu cube by c cube is equal to 1 by lambda cube. So I can write simply lambda cube. And then I have, so what am I taking? Nu equal to c by lambda. Lambda cube. Then I have d lambda by. So d lambda I'm just carrying over from here, so don't get confused. Then I have e to the power h nu, so then that becomes hc by lambda kt minus 1. And I have d. So I had hc cubed by lambda. Oh, I had an h nu, so that has to be written as well. Right. So this is equal to. It's not scrolling again. Okay. So this is minus 8 by h c. So hc by lambda to the power 5. 1 by e to the power hc by lambda kt minus 1 into d lambda. Okay. So here we have a little bit of a strange thing. We ended up with a minus sign, but we simply ignore negative sign as u lambda t cannot be negative. So this sort of tells you it's a difference between like going from nu plus d. Nu is like going from lambda to lambda minus d lambda. So that's why you have ended up with a negative sign. But you can simply ignore it for the purposes of deriving Wien's law. So then u lambda t is equal to 8 by h c by lambda to the power 5, 1 by e to the power h c by lambda kt minus 1. Okay, now our task is to find the maximum of this function. So I want to find out lambda max. So I do d lambda, okay, of u lambda t. So this is a little bit tedious because there are so many terms. So this is multiplied by, I'll write this on the next line, I hope. This is multiplied, okay. So minus 5 by lambda to the power 6 multiplied by this factor, which is unchanged. And you have another term, which is plus. So 1 by lambda to the power 5 is unchanged, and I'm differentiating the exponential term. So that is minus 1 by e to the power hc by lambda kt minus 1. to HC by lambda kt or HC by t minus 1 by lambda square e to the power HC by lambda kt.
Ma'am,
Yeah?
can you please increase the thickness of the pen?
Yeah.
Thank you, ma'am.
This one. ওই হাম্পিটেনের বাম দিকে আছে এই দিকে ওই র্যাকেই আছে গোল্ডেন okay yeah just I wanted to fit it in so I reduced the thickness 1 minute so AC by minus 1 can you see okay I'll before I upload the notes I'll make this a little bit neater it's difficult to read at the moment. So I've just differentiated this again. And then I'm going to set this to 0. Of course, if I set d lambda u lambda t at lambda equal to lambda max is equal to 0. This implies that these two factors that I have obtained by differentiation, they are equal. So that is 5 by, and it will not fit. Let's see, 5 by lambda to the power 6 into e to the power hc by lambda kt minus 1. This is equal to, so this is a positive term. There are two minus ones. Okay. So this is 1 by lambda to the power 7 hc by kt. This one. And I have e to the power hc by lambda kt on top. And e to the power hc by lambda kt minus 1. Oh, sorry. So there would be a square over here. Square. Okay. So this is clear. I mean, it just looks a little bit ugly, but what I'm doing is quite simple. I'm just differentiating the two terms. So in the first term, I have differentiated this part, and in the second term, I have differentiated this part. Just looks a bit ugly. Now, since lambda is not equal to 0, okay, and e to the power hc by lambda kt minus 1, this is also not equal to 0. Since they are both not equal to 0, my maximum point is basically where 5, so which means if lambda is not equal to 0, then I can cancel lambda to the power 6 on either side. Okay. And I'm left with 1 by lambda over here on the right. And I have hc by kt. E to the power hc by lambda kt. And the second condition, that e to the power hc by lambda kt minus 1 is not equal to 0, also means that I can cancel one factor from either side. And I'm left with only 1 on the right. Okay. Fine. But now again, you see this is a little bit of a different from what you have been doing in math. So here you have lambda, of course, but it's a part of an exponential series as well as a part of the multiplier. So it's not straightforward to make lambda the subject of the formula. So this is still sort of looks like an equation which you have to solve for lambda max. So to do that, we say let x be hc by lambda k. Then if 5 is equal to x into e to the power x by e to the power x minus 1. Okay. Then 5 by x is equal to e to the power x.
Ma'am, what happened to 1 by lambda?
1 by lambda.
Ma'am,
Yeah.
you said
This whole thing is x.
okay.
hc by lambda k.
Okay.
So 5 by x is this. Then I can make x the subject of the formula. So x is equal to 5 e to the power x minus 1 by e to the power x, which is 5 into 1 minus e to the power minus x. Okay. So now we have to solve. So this we will solve in sort of an iterative way. If you have not, if you haven't heard of this term, then let me see. In general, so this is like a formula which tells you how to iterate x to get an answer. I'm not sure if you have encountered such procedures. Okay, so we'll do a limit.
Can you please repeat the name of the formula again?
Iterative formula.
Okay.
If I'm not sure you've come across this, so you all are in second year, so maybe not. So let me do a limit first. Okay, so let's do. So let's say if x is small, then what happens? Then we can ignore e to the power minus x. Okay, and what do we get? So if x is small, then e to the power minus x is very, very much less than 1, which means we basically ignore it. So this is the, so what does x small mean? X small means...
X has to be large, right? It's e to the power minus x.
Yes, ma'am.
X
Or
has
else
to
e
be
to the power
large.
minus
Okay,
x
okay,
becomes
yeah.
closer to 0.
X has to be large. Which what I meant was that lambda. No, wait 1 minute. X that is. So we want the, if x is large, yeah, x has to be large. Yes. So if x is large, then e to the power minus x is very much smaller than 1. Then I can ignore it. And then I get x is equal to 5. Which means that hc by lambda max kt is equal to 5. And then lambda max t you can evaluate as hc by 5k, and you will get some sort of constant value. Okay. I think, wait, let me just look up the value. So if you evaluate this, you will get something like 2.87 something into 10 to the power minus 3 millikelvin. Okay, so this is Wien's law, right? So this is a constant. So we have verified Wien's law in the limit of large x. So large x means then small lambda, because x is hc by lambda kt. So x large means lambda small. So in that regime, we have verified Wien's law. Now, if you want to do it for all frequencies, for all regimes of lambda, then let's see what we can do. So then the next thing we can do is we can adopt an iterative procedure. What does that mean? An iterative procedure is where you pose a problem as x equal to function of x. Okay? And once you do that, then you take a guess for x, okay, and you say that is your guess value. So we can call that the iteration number 0. And then you evaluate. Then you evaluate function of x0 and you get x1. So this is called the first iteration.
Ma'am, we guess the value of x to the power 0.
It's not to the power.
Oh, x0, okay, the first term.
The first one, yeah.
We guess that, right?
We guess some value for x and you evaluate this function of x, okay? And that is equal to the sort of first corrected x, which we say first iteration of x. Then, in order to obtain the next correction, you evaluate function of x1, okay? And then you keep going, and at each stage, you see the difference between the you check the difference between the answers that you get, okay? And then at some point you will see that the values are not changing so much. So when values don't change anymore, xn don't change anymore up to some sort of confidence level that you want. So let's say I want up to third decimal place, then I check up to third decimal place, up to some level of accuracy. Then we say that the value of x has converged. And this is then your answer. This is your answer. Because you want an x which satisfies the relation x equal to fx. So if your x equal to fx is satisfied after going through this procedure several times, then you have obtained the answer that you want. So this is called an iterative procedure. It's very commonly used in numerical methods, especially when you're coding things, because most equations you cannot analytically express as x equal to something. As soon as you have like in our case a mixture of exponentials and algebraic functions, you cannot simply find out the value of x. It's also the same if you have some sort of cubic function or x to the power 4 function, then there is no analytic answer to your equation. So then you adopt an iterative procedure. So what was our equation? So our equation was x is equal to, now I have, so let's see.
But it will heavily depend on what our f is, right? If it actually converges or not, or something. I mean, it will depend on our f, right?
There are certain conditions on f, yes. For example, if you don't have a unique value for x, for example, then you will not converge it. But in most cases, you will be able to obtain answers. If you have like I said, if you have many values of x, or if the function of x is really complicated, it is possible that you don't get convergence. In our case, it's not a very complicated equation. We will be able to get an answer.
Okay.
Ma'am, can you scroll up a little bit? Yes, ma'am. Okay,
This
fine.
one?
Thank Yes, ma'am, done. Thank you.
Okay. So this is the equation we want to solve. Okay, and we have obtained one value of x as 5, remember, in the limit. So we'll use that as our guess. So a reasonable, and it also depends heavily on how reasonable your guess is. So if your guess is really very, very far away from what the actual answer is, you will not be able to get convergence very easily, or it will take very, very long. Like you'll have to go to hundreds of steps. So it's important to get a reasonable guess. So in our case, a reasonable guess of x is 5. So we can start iterating. So okay. If you start, well, you can do this later because we will need a calculator for this. So you put x equal to 5 first, then you find out the value of x from this expression. Then whatever x you get, you evaluate 5 into 1 minus e to the power minus of that number, and you continue till it converges. So for now, I'll just give you the answer.
Ma'am, in place of xn, we'll write 5.
Yeah.
Okay.
And then whatever answer you get, next time you put that in place of xn. Fine. This should converge to something like this value, 4.965. This is also sensitive to how many decimal places you keep at every step, etc. So numerically, it's quite challenging to iterate different types of equations. And when you go for research, you'll see that almost all equations need to be iterated to get an answer. So it's an important thing to know. And once you get this value, then we get lambda max t equal to hc by 4.965 into k. And this should give you something like this. Meter Kelvin. Oh, I think I said millikelvin before. It's a meter Kelvin, of course, because lambda is meter and t is Kelvin. Okay. So that is
Ma'am,
it. Yeah.
we can say that the maximum energy is 5 times the average energy. And does it have any relation?
The maximum energy is 5 times the average energy. Why are you saying this?
I mean, hc by lambda is equals to 5 kT.
But hc by lambda kt is not my average energy. My average energy has an
Ma'am, kT is average energy, right?
classically, yes, but not in Planck's law. In Planck's law, it is multiplied by this exponential. So
Yes,
this is,
of course.
yeah. So in Rayleigh genes, it's kt, but in Planck's, it is this factor. Okay. So this is then a derivation of Wien's law.
Ma'am,
Yeah.
I did not understand that step, that this converges to x equal to 4.965. How did we get that?
If you actually do the procedure, so I didn't do the procedure, I just gave you the
Okay, okay.
answer. Yeah. So if you do the procedure, because I need a calculator and it will take some time to do this now. That's right.
Okay, ma'am. Sorry, sorry.
Okay, so then so I'll give you a small assignment for now. So after Wien's law, so let's say assignment 1. Maybe you can derive Wien's law from Planck's law in the frequency form. Okay. So I went over to the wavelength form because Wien's law is reported in the wavelength form normally. That's how he did it. And also this relation was an empirical relation in the sense he fitted the experimental plots to obtain this lambda t equal to constant relation. So it makes more sense to go over to the lambda picture in Planck's law before deriving it. But it would be interesting to see what happens if we do find out the Wien's law from Planck's law in terms of frequency. Okay. So of course this will mean nu min, right? Or so do you think it will mean nu min? No, it will still mean nu max. Okay, because the thing is, it is the maximum spectral energy density, and you're only finding out the corresponding wavelength or the corresponding frequency. So you still
I mean,
call
it is
it
like the
nu
most
max.
probable. It is the most probable kind of thing, right? Like
Yeah, it's the most probable kind of thing. Yes, yes. So don't try to find out the minima or something. Try to find out nu max. And then see if it matches, if you just replace lambda max with C by nu max. If everything was perfect, you should get the same thing. But there is a surprise there. So I just want you to try this out.
Ma'am, do we need to submit this or it's like just for practice?
You can, let's see. Okay, just do it. We'll discuss in the next class. You don't need to submit it. It's fine. Because this is not exactly a question. I mean, I want to point out some things after you do it. But please do it. It's quite interesting to do it. And and you can also take an example over here. So following this, you can compute lambda max at a temperature of say 4000 Kelvin using Wien's law in the frequency picture. And then you can compare with what you get using the wavelength picture. Okay. And then I will discuss this afterwards.
Excuse me, ma'am.
Yeah.
Ma'am, for deriving Wien's law, can we proceed in a manner like we do for kinetic theory of gases, where we find most probable velocity from the distribution itself, rather than taking the derivative? Like for average velocity, we integrate the velocities times the probability for it having that velocity divided by the total. So similar way, can we do the same and get lambda max out from the distribution formula itself?
No, you cannot. I mean, here the maximum means the maximum at which, like the max wavelength at which the maximum energy is emitted. So you have to go over to energy before you can. So it's not the most probable wavelength emitted by the black body.
Okay.
That doesn't contain temperature, for example.
Okay.
So you will not get the right answer. You have to go to the energy.
Okay.
So I'll call this homework, okay? Just so that you don't get confused. So this is not a formal assignment. I'm not marking this on it. Okay. So there is one more derivation. Is it too much? Okay, this is not so... No, I think I'll let you go for today. Today we've done a lot of heavy derivations. You can use the rest of the time to actually work this out if you like. So we have 20 minutes. Then maybe you can start now. I'll wait. So try to derive Wien's law from Planck's law in the frequency law. Just start, then I can clarify whatever doubts you have before you start.
Ma'am,
Yeah.
I had a question in the Planck's law derivation.
Yeah.
Ma'am, didn't anyone question Planck that why did he use Boltzmann distribution?
So, I
I mean,
don't know that. Maybe someone did, but it's possible. I mean, if it struck you, it may have struck other people as well. But nothing better was known at that point, remember. So until you know something better, and since this is satisfying all the observations, I think most people would have been happy to have something that explains experiments. So people actually went into accepting quantization of energy from Planck. So there may have been questions, of course. I mean, or maybe even Planck himself realized that it's possible that there are that the distribution is something else. But I cannot say that. It may be.
okay.
But like I said, later on, people did realize better ways of doing this.
Ma'am,
Yeah.
ma'am, can you go to the part of Planck's spectral density, energy density?
Planck's spectral energy density. Okay. So just the expression. So this one.
Yes, ma'am. A bit up, maybe.
More
A
up.
bit up. Yes. Yes, here. Ma'am, here you have written cross average energy per mode. What is that? I didn't get.
Oh, I'm multiplying it with the average energy per mode. So to get the spectral energy density, I am counting the number of modes in the range nu to nu plus d nu and multiplying it by the average energy per mode because I need to get an energy in that.
Oh, okay, okay, okay.
Yeah.
I have got it, ma'am.
Yeah.
Ma'am, we differentiate this spectral energy density, this Planck equation, and we equate it again.
Yes.
That's what.
Yeah. The procedure is straightforward.
Ma'am, can you show it? Can you show the Wien's law with respect to the lambda once?
It's just lambda max in T equal to constant. Wien's law is not. It's just this. So if lambda max T is equal to constant, then nu max T is also equal to constant. Some other constant, but some constant. Well, not nu max,
Ma'am,
some
do we get a
slight
similar,
max.
ma'am, do we get a similar kind of expression just with 3 in place of 5, something like that?
You get similar type of expression.
I mean, for the appropriate x, not like x equal to h nu by kt.
Yes, it's possible. So actually, I
No,
have not
the question was
worked it out right now. So I will rely on you to tell me the expression.
Ma'am, ma'am, I had a small doubt. And here we are writing lambda max into t is equal to constant, right?
Yeah.
So, in terms of frequency, when we will write it, it should be c by nu min into t is equal to c. So, why aren't we taking like that?
Why are you taking like that?
Ma'am, you
I'm not
asked us
saying it will be nu max into t equal to constant. It will maybe be t by nu max equal to constant. But it will be a similar relation.
yes, ma'am, that's what, yeah, thank you.